from APL.
All right. Good morning, everyone. This talk will be on performance analysis of standalone and in FPGA soft LEON3 processors. So this was mainly an internal research project here at APL, looking at what the current state of various benchmarks is on the Leon processors, and specifically looking at soft processors and FPGAs. So we'll talk about the general process of how you choose a processor for a mission. Then we'll go into which benchmarks and test targets we executed on. Talk a little bit about the LEON3 processor family, the RTG4 FPGA that we were deploying to. Then introduce our own APL single board computer here that we've been testing with. And then the bulk of the presentation will go into the actual performance metrics and the results that we've collected from these tests. I'll conclude with some design considerations to take into account when you're working with soft-core processors, and just give a couple of words on the big picture for processing capability in general. Okay, so when you're considering a new processor for a mission, one of the first questions that comes to mind is, how would this processor compare with what we have done in the past? So you probably have a reference mission that you have run, and you may have done some benchmarking there, and you're happy with the results. And now either the mission requirements for a new mission are more stringent, and maybe you have to downsize the processor, or maybe you're moving up to a more capable processor and you want to put more in it. But the main question is, how does it compare to what we've done in the past? And this leads to other questions like, does the manufacturer provide benchmark data? Is it per megahertz, or is it for peak performance for a given implementation? Are there key parameters like compiler and build options that were used for these metrics? Is power consumption considered? You could run a little faster, but that will cost you in power, of course. And what is the achievable MAC frequency for a particular architecture? Specifically, if it's a soft-core implementation in FPGA, there's other things you have to consider. For example, resource utilization. So you can make a really nice, very high-performance CPU on the FPGA, but it might take up too many resources, and you now have no resources left for other things that you might need to put into that same FPGA. What IP was instantiated when you ran the test? Maybe not everything is in there that you want to test. And of course, again, the timing and the max frequency is very important. Different FPGA technologies would enable the same design, essentially, to reach different target frequencies. So we looked at all of this at some level. One thing to keep in mind is for many CNDH systems that we have right now in orbit and going up, it's almost guaranteed that you have an FPGA in there doing something. Maybe it's for logic, maybe it's for DSP functionality, maybe a software-defined radio. But oftentimes there's space available, and you should consider if it makes sense to embed a processor in there, maybe to augment the capability of that CNDH system. Maybe adding a processor now lets you kick off a hard processor, therefore saving size, weight, and power for the entire system. Certainly a soft CPU would not be as capable as the same level of a hard processor, but if you have the room, overall it might save you some resources in the end. And of course, some of the limitations is the max frequency is probably going to be lower, and as the soft-core IP evolves, there may have not been as many users of this particular version, so some of the testing may have not been as complete as a established hard processor that's been flown on many missions. So we're going to look at comparing performance for a soft CPU versus hard processor, specifically in the Leon3 family. I'm trying to carefully track all these benchmarks so that they're reproducible and that people can compare apples to apples as much as possible. So here's what we ran. We ran some of the synthetic benchmarks. Everyone's familiar with these: Dhrystone, CoreMark, and Whetstone. And then we've also developed some testing applications. They're not really benchmarks, but they help us exercise a particular interface that we're interested in. So we specifically we're looking at Memcpy, for example, to see if we can find a better implementation. And also for a project that we have here, we were interested in performance of NAND flash controller, because we had to talk to a flash device off of the FPGA. And then we also had one application that we threw at it, which is kind of like a realistic, here's terrain relative navigation. Let's see how it does on the processor, how many frames per second it can achieve on different implementation. So this application is a research development right now, so it's not fully optimized, and I will only present normalized values against different platforms for here. Here are the targets we considered. We have the UT699 and UT700 systems from Geisler. The UT699, actually, I treat that as 2 targets because you can test with code running an SRAM or an SDRAM, and this is important because, again, memory is one of the most important subsystems on your CPU, so a benchmark could perform significantly different depending on what kind of memory technology you're targeting. Then we also have the R2G4 development kit from Microsemi, and that lets us embed the soft-core CPU and test that with DDR3 memory. And then we have our own board here at APL called the CORESAT SBC, and that lets us target the UT700 hardcore CPU as well as instantiating our own soft-core Leon design in the FPGA. And both of those target the same type of SRAM, so we can compare results between the two. A little bit about the Leon processor. As you know most of these things probably. 32-bit processor, SPARC V8 architecture, AMBA 2.0 bus interface, runs RTEMS, Linux, VxWorks, other operating systems too. The systems we've considered, the UT699 and the UT700, these frequencies here, 66 and 166, these are the, in the data sheet, these are the max frequencies that these processors could run at. Here are some cache specifications to 8 kilobytes for 699 and 16 for 700. For the single core, everything is configurable about it, including the fault tolerance. In our case, we used a commercial version of the code, so we didn't enable the fault tolerance. Performance should be similar, though, although the area will grow, of course, if you enable fault tolerance, the area on the FPGA implementation. Well, some things we can customize is whether the FPU is on, what kind of FPU, what the cache size is. Perhaps you want a larger data cache than an instruction cache. That's possible. What kind of memory controller is used, what IP. So it's all kind of, it becomes a very large computer architecture problem, and you can really customize it specifically for your application. Also, what's very nice is you can build multiple CPU systems out of this. This is actually the subject of an internal research effort that we have this year, looking at multiple core embedded in the FPGA using RTEMS SMP and OpenMP to accelerate a specific algorithm. But one key parameter, though, is the max frequency. Again, it depends on the FPGA target technology, so it's very likely that you won't be able to reach the same 100 megahertz or 150 megahertz level as you can with the hard processor IP. Okay, so this is the Microsemi R2G4 RadTolerant FPGA that we were targeting. Basically, what I wanted to show here is this FPGA, and there's others too, like the Xilinx Vertex 5, for example. They're significantly large now. You could embed multiple CPUs in them. They have a lot of embedded memory components from which you can build cache and internal memory. So this is really the driver for why embedding processors now is a fairly good opportunity, and there's likely that you will have space in many projects to be able to accommodate for a processor in your FPGA designs. This right here is our board that we were testing on. This is an internally developed APL single board computer called the CORESAT SBC. It fits into a CubeSat, but it's also meant to support many of our missions here. One of the key goals of this was to make it low power. I think the power estimate is about 4 watts for this board. And it comes with things like, of course, the R2G4 FPGA. We have volatile and non-volatile storage on this board, MRAM, SpaceWire, and there's also some radio components that help you build a radio out of it. So very nice system. You can also, from my point of view, this is interesting because I can build a very interesting computer architecture on the FPGA, targeting multiple processors, putting customized cores in there, and basically it's a very good test platform to develop these high-performance designs. And we are using this on an upcoming mission here for DART, this particular single board computer. Okay, so our test configuration, as I mentioned, includes a number of boards. I threw this slide in at the end. I realize it's probably important to document the various memory interfaces, because you'll notice, not all memory is the same between the different systems, and not all systems run at the same frequency. But with this information, you can hopefully get an idea of, well, if a certain system is performing a little better or worse, it could be due to some of the differences in the memory configuration. Most of the benchmarks that I present are reported per megahertz, but I also, when possible, also include information for what the maximum performance at the maximum frequency that the system supports is. And as I mentioned, all our soft systems were built for the non-fault tolerant version. It's the commercial version, although fault tolerance could be enabled at a cost of more resources on the FPGA. Okay, so the first test is Dhrystone, and here you can see, you'll see in all these slides I throw out the important compiler options here and the optimizations that we used. But here what you can see is the soft core processor. This is the bottom two rows here. Per megahertz, it performs fairly well. It actually, per megahertz, beats some of the hardcore processors. But if you consider the max performance at the frequency, so the soft processor, in this example, I can meet timing at about 50 megahertz. You can probably get to maybe 60 if you push it, but 50 is a fairly comfortable number. Of course, if I use a UT700, I can get to 100 or maybe 150 megahertz, so you have to scale that number. But all in all, for per megahertz performance, it does fairly well compared to all the other Leon architectures and beating the UT699 and coming very close to the UT700. For CoreMark, it is also similar. Now, what you'll notice here, though, is there's a big difference between tests that we ran on the UT700 development board from Geissler versus our own SBC product here at APO. And the main difference there, and we're still investigating this, is the same CPU, it's different frequencies. That's okay, we're scaling per megahertz, but there's different memory. One is SDRAM and one is SRAM. So depending on the application, depending on the benchmark, if it's more burst-centric, it'll probably prefer SDRAM than SRAM. If it's more sporadic access, it'll probably prefer SRAM. So we still need to get to the bottom of that and see where the difference is coming from, but it's likely because of the different memory that we've used. The rest is very similar to the previous. This is integer performance test. The soft core slightly outperforms the UT699 on the per megahertz basis. For floating point, the Whetstone test, this was quite interesting because we were able to test different implementations of the floating point unit, both the full floating point unit, and there's also options to drop in a lighter version of the floating point unit with different configuration settings, or no floating point unit, and do emulation. Certainly, if you have floating point tasks, you don't want to be down here. If you have a couple operations once in a while, that's okay. But if you're doing something large, you need to put a floating point unit in there. It does cost you resources, and I'll present that at the end, what the cost of the floating point is. Otherwise, for a light unit, you can see the difference is, there's some difference here, but it's not as big as going between no floating point and having a light FPU. And then there's a jump between having a light floating point unit and having a full floating point unit, but you also see that there's a large jump in resource utilization as well. Per megahertz, if you take the soft core with FPU system, it compares fairly well with other Leons of the same family, UT699. This is the same development board, but using different memories. And this is the UT700 on our board. Again, there's this difference here, and this is likely due to memory, but we're still investigating what this difference is due to. Memcpy. So this was quite interesting and surprising for us. So we were looking at CPU utilizations for a certain project here, and Memcpy is something that's used very often. So we started poking around at the Memcpy implementation. So it turns out that Spark processors have a hand-optimized assembly version of Memcpy floating around in the Linux build. And here's a link here for where you can find it. If you look at the code, it's very nice code. It's very nicely written. There's very deep pipelines of double loads followed by double stores, and it really saturates the pipeline and tries to move data very efficiently. Well, it also does alignment, so that if you're trying to copy memory that's unaligned, it brings it into alignment first and then tries to copy it. Now, of course, you shouldn't be copying memory unaligned. You should always make sure your memory is aligned. But if you do, this was a very interesting data point here. So using the, so we call this optimized version new copy, for lack of a better name. Using the hand-optimized version of Memcpy, this is the time we get for copying 4K of data, and cache is off in this case, compared to using the built-in Memcpy provided with GCC or RTEMS. This particular test was run with the BCC compiler. We also have very similar data for RCC. I didn't throw it in here. But even for doing aligned copies, there's a slight preference for doing the hand-optimized aligned Memcpy versus the unoptimized Memcpy that comes standard with the compiler. I mean, this isn't too big of a difference, but here it's quite large. So point of the story is, for some of the work that you might be doing, consider using this version of Memcpy, see if it makes a difference. It may not make a difference for you, especially if you have aligned copies everywhere, but you might be surprised. Then we did some tests on flash performance. So for one of our projects here, we have to use NAND flash. This is due to higher density, faster program times, and generally it also provides better radiation performance. The downside is that it's a much more complex interface. You have to request a page, you have to read a page. It's not as simple as NOR flash, where you can actually just tie it directly to one of the hard Leon processors. So you can't connect a NAND flash controller to a hard Leon core, but if you had a soft Leon core, you can drop in the NAND flash controller IP, and then you can talk to the NAND flash controller. So we did some tests, and here are the data points here. We're able to get to, in this particular implementation, to timing mode 1 for this chip, which gives us about 96 megabits per second of throughput when we're doing a program, which we're mainly recording on the fly as we're collecting data. So this was the important metric for us, the record. The limitation here is mainly due to the frequency. So the soft CPU, we can't clock it faster than 50 megahertz in this implementation, and the IP is running off of the same clock, so that factors into how fast the data commanding can be issued to the flash chip itself. But this is the type of things that you can't do with a hard processor, and you have to throw it into an FPGA. So having a soft CPU does help in this case. And here's another application. So this is terrain relative navigation. This is something we're working on in APO here. And here I just wanted to show normalized performance numbers compared to the UT699 board. We're still working out on optimizing our implementation of this algorithm. So I'm not showing the actual runtime numbers here. But the results here show that compared to UT699, the soft-core implementation per megahertz actually does a little better. It still lags behind what the UT700 can provide. And for maximum performance, if I take out the per megahertz, you can see the UT700 still does quite well. But the soft-core comes in fairly close to the same performance as a UT699. And keep in mind, this is running at 50 megahertz, and this is a 66. So it's doing a little bit better as well. Okay, so this is quite important. What does this cost you, dropping in a soft-core processor? So we measured the utilization in FPGA resources, lookup tables, flip-flops, micro SRAMs, embedded RAMs, DSP units, and clock units. So depending on what kind of system you build, for example, if you have a basic system without an FPU, you're looking at somewhere around 8% of lookup tables on the FPGA. That's fairly small. I believe this is just using one clock unit that can be shared with other subsystems as well. But if you start dropping in things like the floating point unit, you can see your utilization goes up, and you're sitting at around 17% or so. Still fairly good. So if you had a completely empty FPGA, it's likely you can drop in 4 of these. It's unlikely you're flying an empty FPGA. Maybe you have 50% available. You can maybe drop 1 and have a little bit of margin left for other things. This is specific to our CORESAT single board computer here. We were also dropping in the flash controller. The flash controller itself takes a little bit of logic resources because there's buffering involved. So you can see this design uses some of the embedded SRAMs on the FPGA, going up to about 20% or so. For power, this is just showing the data for the FPGA itself. We didn't have the instrumentation necessary to compare apples to apples with a hard Leon processor, but we can show different power characteristics of different builds that we've done on the FPGA to see how it scales with additional resource utilization and with different applications. So I'm showing 4 builds here. No FPU is the red build, and then it goes up to a build with an FPU, SRAM controller, and a NAND flash controller. So when you're idle, the difference is not very much. I believe the clock is stopped to the Leon, so it's not really doing anything. But when you start running it at different benchmarks, you can see some of these values start spreading, and that's because there's more logic that is on the FPGA, more things are being clocked through, so it consumes more power. But what I wanted to highlight here is that the power consumption isn't all that high. The FPGA, if you have the FPGA in the system anyways, you're consuming a certain amount of power. Dropping in a soft-core processor bumps it up a little higher. It's not as much as adding an entire hardcore processor to support your data processing. Okay, so I wanted to just go through a couple things that we've learned through this process and found interesting in the design in the configuration of the soft core. So one thing that was really cool is the cache. So when you start, you select how many kilobytes of cache do I want for instruction and for data, but you also select the associativity, 2-way associative, 4-way associative. So if you think about it, the higher the associativity, the higher the cache, it should be better. There's a very nice book, the computer architecture book by Hennessy and Pedersen. I'm sure many of you have seen it. There's a table in there that shows hypothetical performance of cache size, associativity, and miss rate. And what they show there is that as you get into larger cache size and larger degree associativity, the miss rate doesn't really change very much between 2-way and 4-way. So keep that in mind when you're building a soft-core system. If you say you're going between a 2-way and a 4-way cache, that's only 16 kilobytes, it costs you quite a bit in implementation on the FPGA, but doesn't really provide much of a benefit in the miss rate. So in this case, it makes sense to go with a 2-way cache here. And in many of our designs, we actually went with an 8-kilobyte cache. It's a little more resource constraint. And we went with a 2-way cache because there isn't that large of a difference in the miss rate, and we can really tolerate that for our applications. But this was quite nice to see that there is actually that large of a resource difference when you change the number of ways for your cache. There's also options that we didn't get a chance to look into, but certainly would be very useful. There's the clock to X option to build your system with. If your FPGA target technology allows you to meet timing at a higher frequency, you can clock the CPU at a 2X clock rate versus the AHV bus, and that improves your access to cache and lets you lower your power consumption for the entire system by not having to run the bus at the higher speed. This is something that recently came out of Geisler that certainly would be very useful for instruction for designs that are constrained with their boot area. So there's something called this Rex extension, which encodes the instructions in 16-bit versus 32. And then if your processor has the appropriate logic in it, then it decompresses that on the fly and executes them as Spark instructions. Some of the papers that I've seen shows that it can reduce code by 7 to 15% or so. So that's pretty nice if you have a memory-constrained system. This is a task that we're working on this year. So we're going to continue with our soft-core effort, dropping in multiple cores, but also start looking into putting in SMP RTEMs so we can experiment with OpenMP, specifically for the TRN application. That would be a good candidate. It's image processing-based algorithm. If we can start parallelizing certain tasks in there, then we can really, it would be low-hanging fruit to get better performance if we can use multiple cores. And the soft core makes it a very nice environment to be able to configure the processor as you wish to suit this application and test this out. And so I want to kind of conclude with this, and I think I have one more slide after this, the big picture. So when I look at the different technologies out there, you have single-core, multi-core, and FPGAs. That's basically what's flight qualified right now. And when you select between those, you have to think about what is the effort to program them and what is the performance that I can obtain. Certainly, if you're trying to go out for very high performance, the best right now for RadTolerant implementations would be an FPGA. You can do a custom design. It takes a lot of effort, and it's not very general purpose. On the other end of the spectrum, there's a single core design where it's much lower effort, but you're probably limited by the performance that that core can achieve. Somewhere in between is the multi-core approach, where the effort is much lower than doing a full custom FPGA implementation. There's more rewards than doing a single core, and it still stays fairly general purpose. So at APL, with our CORESAT SBC design, we're kind of operating in this domain where for a particular project, we can choose which way to go. Perhaps sometime in the future, we'll have availability of GPU and neuromorphic computing, where you can really reap the benefits of high performance, and especially in the case of GPUs, the effort will not be as complex as doing FPGA development. Finally, to conclude, so some things that I want to leave you with. So mainly the soft-core processor, it can be configured to meet or exceed the per megahertz performance of a hard LEON3 processor. Keep in mind that the max frequency of a hard CPU is much faster, much higher. So that's a limitation. Again, though, most missions have an FPGA on board, so consider putting in a soft-core processor if you need the additional capability and if size, weight, and power is a constraint. Pay attention to your memory. This affects performance quite a bit. Memcpy. This was quite an interesting result for us this year. If you're looking to optimize somewhere, try the optimized version of Memcpy, see if it makes a difference for your application. And then another thing to consider for floating point unit, especially for the soft-core design, there isn't just one flavor. There's multiple flavors and there's options, and that the trade-off there is utilization. So pick the one that you need for your application. Don't over-design. And then hopefully by next year, we'll have some more information about multi-core and performance on SMP RTIMs. So that's it.
That was very good. We have one more presentation after this. And any questions right now?
Yes.
Yes, a couple of notes. I saw you presented the weight states on the SRAM.
Yes.
That's nice, but then also there's a second relation which is interesting, the system frequency on the STRAM bus versus the system frequency. That also affects in that case.
Yes, of course. It's a combination of both, of course.
Yeah.
You want to find the sweet spot between the lowest number of weight states and the highest frequency.
Yeah, and it might be difficult to compare the results when some of the applications fit into cache or partially fits into cache, whereas some doesn't.
Yes.
And then you might think that it's depending on the memory bandwidth, but it's not.
Right.
So that's I think important to point out.
So we were cognizant of that when we were doing our Memcpy performance tests. We did turn cache off for that.
Yeah, I saw that, and that also affects. I mean, if you turn off the cache, then if you do an underlined access of a word, then that means 4 byte accesses.
Yes.
So you multiply the differences of a bad Memcpy to a good Memcpy by turning off the cache. So then the differences is multiplied by 4 basically. And then also that another factor there is the relation between the system clock and the memory bandwidth.
Yes.
So it might be quite hard to compare the different cases in that case. And also a last note about Memcpy. That was news to me, but then I think in VxWorks this has been addressed. So I think in VxWorks the benchmark of Memcpy does not have this problem.
Okay. Okay. Yeah, I haven't tested it on VxWorks. This was, the standard Memcpy that comes with GCC and RTEMS versus the one that's out there for Spark. So it'd be interesting to look at Solaris, for example, to see what they used back in the day.
Yeah, and they might also have a different license of their Memcpy.
Right.
The Linux Memcpy, you should be aware that it's GPL.
Yes.
Okay.
Maybe it was in the presentation, but do you happen to look at flops per watt or ops per watt for hard versus
No,
soft?
no, I haven't brought that out. I think we might be able to. So the power data came at the very end, and we may be able to scrub through the data we've collected to also have that included. But we have not looked at flops per watt. No. It's
I
important.
guess
you're
that's it. Thank you, Dmitry.
Very interesting.